Hello everyone. In the previous discussion, we can have a function mapped from a single random variable, but this time we have two random variables and map it to one function. For example, z. Z actually can be mapped through x and y, right? X and y through function g to z. And again, we want to know, can we find the PDF of z? Alright, given join PDF of x and y. For example, how about the example z equal to sum? Of course, we can have some physical meaning. Why we have z equal to x plus y? Alright, but here I skip the physical meaning. For example, you can check the possible physical meaning like this, and so they can have the relationship z equal to sum of x and y. Well, therefore, we want to know, it doesn't mean we want to find the relationship sum of x and y. Possibly you can have a difference, multiplication, ratio, or maybe it's the inverse tangent. Sometimes we want to find the angle, and the square root of this, this one sometimes it says as we have the magnitude, and we want to find the minimum value between x and y and maximum value between x and y. Alright, so all possible function, if we want to use it, and then we can have the derivation possibly. But later we choose some to illustrate how to have the derivation CDF of z, and then still want to find PDF. Therefore, we still have the general approach, derive CDF, and then we want to have the PDF. Well, so how to have that? It looks like, oh, okay, we can have a value in terms of z, but value in terms of z can be specified by x and y. So x and y, then we will have a region. Alright, if we have x and y, so in terms of x1, it should be a region. Once we find the region, so it says the corresponding probability can be collected through double integral. And we can have the corresponding probability for the CDF. So this is the idea. Can we find the region? Alright, so can we find the region? Of course, we don't have the same. We have a different one. But right now, we have the general shape or irregular shape to denote the region, possibly. Well, yes, we find possibly the example z equal to sum of x and y. Alright, so z equal to x and sum of x and y, so something like this. Alright, so the slope should be, look at this, if we have this and treat this is a constant, and so that y equal to minus x plus z. So the slope is minus 1. So that's why we will have a line like this, because we consider region in terms of x and y. Alright, so here it says we have this one, says this one, and then this is a region. Alright, so this is a DZ region. DZ region, then perform integral. How to do? Actually, we can have a y first. Y should be the outer one. X is the inner one. So inner one should be relation to z. So actually from negative infinity to the current x. So current x is z minus y. And for the outer one, it's y. So of course, we have the whole range from negative infinity to infinity. So based on this one, of course, we can have dz, and dz to the proper range of y and x. So this is the first example, sum. And actually nothing wrong, but sometimes I use the Microsoft 365, so it doesn't follow my way to show the result. But I will provide you the slides, I mean the PDF, and so that you can use the slide to check should we have the correct results. If yes, and then you just follow that correct result to check. But you can try to find it if you can shift it. And right now, find the probability through double integral for CDF, and then we can apply the second step, differentiation. So by differentiating CDF directly, so we can have a PDF. And how to do? Here maybe we have the complex discretion due to Leibniz, but it won't be necessary to have that. Let me show you how to have that differentiation, right? So this one, differentiation, then because of x and y, but we need to perform differentiation. So here we use the concept partial differentiation. Partial differentiation, where we have a variable here. If we have a variable here, how to have the result? Actually, it's just a chain rule. Using chain rule, okay, I can define variable, for example, z prime equal to z minus y. So chain rule says, oh, okay, we can perform this through dz prime, but multiply dz prime dz. So this one, dz prime dz, this one, the variable here, this is a constant, so it's 1. And so that if we have a dz prime, this is a variable, through the theorem of calculus, then we can have the results. Oh, okay, this one should be the inner one, but differentiation with respect to this z. So this is the current variable x. So we have x substituted by the current one, and the others vanish. So we have this z minus y and this, but we still have a 1 integral here. So that we have the result. Let me erase O to have the results. How I reach the result? Actually, I pass on chain rule. And so that I can have the results. It doesn't mean we need to have the complex reason of derivation. We still can have the derivation. And likewise, you can show we can have a different way to express the result. Oh, in terms of x. Alright, so you can have a different way to have the result, but I don't know. Oh, okay, if we consider the example, z equal to x plus y, then we have the formula. And actually, we can apply the concept to have the formula. We just want to let you know what is the formula if we have the example. Sum x plus y, then we have the formula. Alright, so I don't know the next results again. Right, so we can have the alternative to have the result through integral with respect to s. So this one, same. And you can check how about they are independent. So independent, so we have this. Independent, the form here, it's specific convolution. Alright, so if it is convolution, then we have the conclusion. Two random variables are dependent, then density of their sum, it should be the convolution of the two random variables PDF. And furthermore, we can have the special case. If as lower than 0 for non-negative part, we don't have the probability. It says it should be 0. And so for that case, previously we have this. For example, in terms of y, right? So this one, non-negative, so larger than or equal to 0, larger than or equal to 0. So finally, we have the range y lower than 0 or greater than 0. So that's why we have this. So it doesn't mean we need to have the further derivation. I just that you have the constraint. Because of the constraint, so easy, we will have the non-negative range. Oh, sorry, non-zero range. Alright, so based on the concept of a non-zero range, then we have the result, and that's it. Right? And likewise, you can have the result for alternative form. Same. Well, right now we assume the two variables are exponential. So how to have the result? Exponential. Alright, so if an exponential, what is the form of exponential? This form. Exponential, exponential. I skip this u because we just didn't know non-negative. And the common parameter here, common parameter lambda in terms of form. And if this is a common parameter lambda, and then sometimes we should know mean. Mean should be equal to 1 over lambda. But right now we don't mention any mean, so we don't have a parameter lambda. And the parameter lambda actually it's the form here. If we have that one, sum. Oh, okay, follow their formula, this formula. So which formula we want to apply dx? So we have a dx here. And so fxy x z minus s. So that's why z minus s. And rearrange it so that we can move constant to the outside. And here it's 1. So finally it's z. So we have a z. And also it's non-negative, so of course we have u, but we remove it so that we have the equality. But you have u of z. It's somewhat strange because finally, if we want to have the result, it should be negative part is 0. Now negative part is the current form. So finally, we should multiply u of z here. All right. So this is exponential. And last one, we apply the result to uniform random variable. All right, uniform random variable. Then we have the case here, uniform random variable. And this one, we want to derive from scratch. That says from the beginning, the very beginning. And then we can have the following derivation, CDF, if we have region 1, and CDF if we have a region 2. Alright, and again, once we find it, so through differentiation, so we have the form here. So this one follows CDF first, and then PDF. You can try it later, and so that yes, we have the result. But we can have the direct convolution. And direct convolution, we base on the direct convolution. Alright, direct convolution, region 1 and region 2. So we have first one, second one. Okay, region 1, region 2. Same, we have the result. So this one, apply formula. Alright, apply formula, then we have this. I skip some details talking about the formula, but you need to have this. But have this. In fact, we have a function talking about shift and reverse it. So talking about reverse it or something else. Alright, so the current figures actually want to show you, the formula 1, formula 2, and multiply, so we only consider the region. And this one only consider the region. So I go through quickly, but let you know the key points. And You can check it later. And so that yes, we have the results for case 1 and case 2. So case 1 and case 2. See? And case 2. So that's why we can have this if we care about non-negative region. Well, if we have that one, look at this. The current PDF, what's that? It's the triangular distribution, this one. So it says uniform. Uniform, independent uniform can reach triangular. Alright, triangular distribution or triangular random variable. So this is the possible fact we can reach. And next one, how about difference? Difference actually, you still can follow the same way like this. And you can derive it so that you can have the result. Previously we have z minus y, but this time z plus y, or maybe x plus y. But we use z plus y and we show the others. Okay, so for this I think it says if we want to know the formula can be derived easily. And next one is ratio. Sorry, maybe because of the shifty formula. How should I know? I have the line up result, but I use Microsoft 365, but I cannot control the position. It still go to the wrong position, but it doesn't matter. So for this, you can follow the description to have the region. Finally, I just want to let you know ratio. This is the derived formula. Alright, based on the derived formula, then you can apply the different example. Here we have example 8.5. Given joint normal. What it means joint normal? This is the joint normal. And how to have the ratio z. Apply the formula so that we can have the results here. Once we have the results here, someone want to have the name for this. It's Cauchy random variable. So you can check it. And for the remaining, actually, I may skip the details. For example, square. About square, how to have a square, you can map it to square. Variable 1, map it to square. Variable 2, and here it's sum. So you can have a multi-stage. Multi-stage transformation, then you can have the result. But you try to have the direct result, so I skip the description. And likewise for this, I skip it. Here we have this. It's a different one. It's minimum or max. Also the range. And this kind of formula actually we want to let you know order statistics among a variable. Here, order statistic. Alright, about the order statistic, later we consider n equal to 2. For max, alright, for max, actually we want to know the results. CDF first. So max, right? And actually we can assume, how about this relationship and how about this relationship? If it is max, so it's x. If it is y, so y max. Alright, so here we have the region. And the region, then we have the reduced result. It should be the union. Union, so change union to sum. And so that it says, right now we have this. We have equal. This is equal. Alright, equal then this one, it should be a region. All right. And this one, another region. And actually, if we have the condition x lower than or equal to y, x lower than or equal to y here. And this one, x greater than y. All right. And if x greater than y here, so it says it should be given x lower than or equal to z. So, for example, this equal to z. So, z and this region, all right, cannot exceed this one. Likewise, z here equal to y, so it should be the same point, z and z. So finally, we have the region. All right, if we have the region, put them together, we have the region. So it says, oh, okay, the total region, this one should be this. Join CDF and put Z and Z. So this is a region, the probability. All right, why? Because that region says x lower than z or y equal to z. So it should be n, not o. So this is a region. The region here, so it's z and z. And if they are independent, so we have the independent one, and hence we have the differentiations, PDF. So we can reduce this result. Only when they are independent, or otherwise not independent, we have a z and z. And similarly, we can consider minima, and we can have the region. Oh, okay, so if y lower than x, so it should be y. And here, if it is x. And likewise, in terms of w, and w here, so this one, previously it's x greater than y, and this one, x lower than or equal to y. But currently it says x greater than y, so we should have a w, y lower than w. Y lower than w, so here, this region, and another region, and put them together, so here, we have a region. So the current result, we have the region, and to have the region, how to have the results? Oh, that one, it should be W, okay, W greater than, so W greater than, this is W greater than, W greater than W. And solid greater than, so it should be this, 1 minus y. If so, the probability here, how to have the probability? The probability actually says, oh, okay, if so, then something like we have this one. I use a different color. Something like we have the first one plus the second one, but we have the overlap one. First one, second one, but we have the overlap one, so minus the overlap one. The current probability can be interpreted by this formula. All right. Once we have the formula, and then same, we can have the differentiation. If they are independent. Sure, if they are independent. And solid independent, likewise differentiation. So we have the form here. Right? Alright, so this is the final form if they are independent. So for minima and the maxima, we have the independent. But look at this. the older statistics, actually we assume they are independent. So because of independent, of course, we try to have the result for the independence results only. Alright, so we have the two formula, formula 1, formula 2. And right now, we can have the result if we can find minimum, maximum. So multi-stage, you can use ratio. So it asks you to apply multiple results. Alright, that's it. So I think this one, you can check it later. And for the current one, if we have the discrete case, and discrete case we want to find sum. So how to have the result for sum? It says Poisson with the parameter lambda 1, Poisson with the parameter lambda 2. How about sum of the two? If for sum of the two, it says, oh, okay, given sum equal to n, so how about value k and value n minus k, so it's sum n, and if so, they are independent. So we have we can use this to have the partition. Sum of all partitions, that says union. And the union here, they are not of that region, so we can have a summation to get the probability. And also, they are independent, so we have the form here. They are independent. If they are independent, then we can have the Poisson. Poisson 1. Poisson 2. Rearrange it, then we can move constant to the outside. And actually here, we have these. And this one, actually, what's the form? It's a binomial. Binomial distribution. So this one, and binomial distribution. So we have rate 1, rate 2, sum to raised power to n, so we have the result. And finally, what's the form? The form is Poisson again. And follow rate, sum of the two. So that's it. We will have the conclusion. Sum of the Poisson random variables. It's a Poisson random variable again, but the parameter should be the sum of the individual random variables. And that's all. And that's it. So this is the discussion for the advanced materials. And see you next time. Bye-bye.